In this video, we're going to discuss the relationship between motion, internal energy, and temperature. Doing so is going to provide the answer to a little mystery. Let's imagine I have a ball above a table. We know that ball has a certain amount of potential energy because it's at a height above the table. And if we drop the ball, it falls, and we know that just before it strikes the surface, it has a certain amount of speed. And because of that, it has kinetic energy. And the kinetic energy at the moment before impact is going to be equal to the potential energy it had here. So we know that there's conservation of energy. So first we had potential energy, and then we had kinetic. And in fact, after the ball strikes, we know it's going to be squished, and there's going to be elastic potential energy that will be equal to the energy it had at the start, and then it will bounce back up, regain its potential energy. So we'll exchange between potential, kinetic, etc. However, if we watch the path of the ball, we know what's going to happen in reality is that it does this. Each time it bounces a little bit less high than the time before. And so it looks like energy is not being conserved, at least if we look on the macroscopic level of what's obvious just by looking at the ball at a distance. However, if we were to take a very accurate thermometer and measure the temperature of the ball before and after this process, we'd see that the temperature went up. So something is happening to the ball. And so what we say is that the internal energy of the ball increased. So we took the potential energy of the ball at the start, interchanged it back and forth between kinetic and potential, but each bounce, a little bit of the energy is converted into internal energy. So what is internal energy? Well, the macroscopic thing that we can measure with internal energy is that the temperature went up. So internal energy, we're going to use symbol U, although which is usually what's used for internal energy is the symbol, although occasionally you'll see E. So internal energy U is a function of temperature. So basically, if the internal energy goes up, it must be that the temperature also went up. Okay. And you probably experience this yourself in your daily life. For instance, if you use a drill, you'll notice that at the end of drilling a piece of wood, if you touch the drill bit, it's quite hot because you've converted electrical energy that went into the drill into internal energy of the drill. Or for instance, if you were to go down the hill on a bike and use your brakes a lot, if you touch either the wheel of the bike or the brake pad itself, you'll notice, oh, these are quite hot. So you've increased the internal energy of the brakes and of the wheel. So what does that mean on a molecular level? Because we're always interested in chemistry and saying, what are the molecules doing? So what is internal energy? Well, in fact, if we could zoom in and use molecular eyes, we'd be able to see what's going on with internal energy. So let's try to do that using some simulations or animations. So the first type of internal energy we're going to see is rotation. So I'll just write that out here. So rotation is when a molecule rotates on one or more of its axes. And so here we have a model of a water molecule rotating about the axis between the two hydrogen atoms. And so if we look at a molecule that is in the gas phase or the liquid phase, we can get rotations. Now, it's a little bit different in the liquid phase because the liquid phase is kind of like a mosh pit. And so the molecules are going to be banging into each other, and so they won't be completing a bunch of nice, neat rotations like this because they're constantly banging into other water molecules. But in the gas phase, molecules are constantly rotating. In the solid phase, they won't be, of course, because they're locked into a crystal lattice. As we increase the temperature, the internal energy goes up. And one of the reasons that it goes up is that the rotational speed of molecules goes up. So for instance, if we looked at oxygen molecules in a sample of gas at 400 Kelvin, they would be rotating more quickly than oxygen molecules at 300 Kelvin. Another type of motion we see is vibration. So if you imagine we have a carbon atom in a big chain here, we can have the hydrogens. So let's just draw the molecule that we're looking at here. So we'll just zoom in and just look at this one, just these two hydrogens. I'm not going to show the other implicit hydrogens. So these hydrogens can do this asymmetric stretch. They can also do a symmetric stretch, and also we could have vibrations where we, for instance, change the bond angle. So the bond angle goes from being a little bit wider and a little bit narrow than the equilibrium bond angle. So we can have all sorts of different vibrations in molecules. And so this is something that happens in all three states. So in the gas phase, molecules vibrate, their bonds vibrate. In the liquid phase, that happens, and it even happens in the solid phase. So even if we took this molecule, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, so this would be nonane. Even if we took this molecule and froze it, so we had a crystal lattice of a bunch of these chains, the bonds would actually still stretch and compress a little bit in the solid phase. And in fact, if we have a crystal lattice of something like iron, you're not used to thinking of there being motion in a crystal lattice of a solid, like salt or a metal or something like that. But this distance between atoms and lattice is not constant. Basically, the atoms are moving back and forth in the x and y and the z dimension a tiny bit. So where they're vibrating within their equilibrium spacing. So we always have in solids, liquids, and gases vibrational motion. The only exception to that is monatomic gases. So if you have something like argon or helium, since there aren't any bonds, there's no molecules in the gas phase, there's no vibration. The last type of motion we'll consider is translation. So if we had a box of gas, we know that the gas molecules are whizzing around, they're bouncing off each other, they're bouncing off the walls. So just moving through space is translation. So that's the easiest type of motion to understand. So to summarize our discussion of motion, we can say that internal energy is going to be a function of all the different types of motion that we can have at the molecular level. So we can have translation, we can have vibration, and we can have rotation. So if we were to look at our drill bit when it's hot, we know the iron atoms in the steel of the drill, they're not translating because they're stuck in a crystal lattice. And they're point particles, so rotation really doesn't have a meaning, but they would be vibrating within the positions in the lattice. Okay, so we don't want to be deceived by the static images we see in a textbook of atoms. They're constantly vibrating back and forth. If we were to look at, the same would be true of your hot breaks or something like that. Or if we looked at the polymer chains in a rubber ball that gets hot after we drop it many times, we'd see those polymer chains had vibrations in their bonds. So the bonds would be stretching back and forth from shorter to a little bit longer. If we look at a hot gas, let's imagine we look at some water vapor at 400 Kelvin as opposed to 300 Kelvin, we'd see that the water molecules have all sorts of vibrational motion. So we'd have stretching along the bonds, and we'd also have this scissoring motion where this bond angle gets a little bit wider and a little bit shorter. So we'd definitely have vibrational motion, but of course also, as shown in that little animation, the water molecules would be rotating, and of course, since we're talking about water vapor, it'd be flying around the room. So we have all different types of things. And what we'd see is as we increase the temperature, all these types of motion get faster. And so if we were to draw a graph of internal energy as a function of temperature, we'd see that it increases. Because the higher the temperature, the faster the molecules are vibrating, rotating, and translating.